Hello students, good morning. So today we are going to discuss about magnetic field at an axial point of a current loop. So far we have come across only straight conductors. So now we are going to take a current carrying loop. Means generally in electrostatics we call them as rings, but here the same ring, if it is going to carry a current, then we call it as a current carrying loop. Okay. So today we want to see what is the magnetic field at an axial point of a current carrying loop. So magnetic field at an axial point. Magnetic field at an axial point. At an axial point. Okay. Now here when we talk about this electrodynamics, that is moving charges and magnetism, related to Biot-Savart's law. So first we discussed about Oersted experiment. So Oersted experiment, I told you what are the important points. So regarding the Oersted experiment, I told you 3 points you have to keep in mind. Number 1, always the magnetic field line are perpendicular to the conductor which is carrying the current. Number 2 is the magnetic field lines are concentric circles around the conductor, and number 3, the magnetic field depends upon the distance of the point from the current carrying conductor. Okay, that is the 3 points that you have to keep in mind. But after that, mathematical treatment has been given by 2 physicists. One is we have the Biot and second one is Savart. Okay, so Baptiste Biot and Felix Savart, they individually worked to find a mathematical solution for the induction, the magnetic induction or magnetic field due to a current carrying conductor. But related to this Biot-Savart's law, very important point is we should know the vector form also. So before going to discuss this axial point magnetic induction, I will tell you in a simple way how to take that angle theta. We are taking sin theta, no? What is the magnitude we have taken due to a current element? So due to a current element, we know the magnitude of the magnetic induction dB is equal to, we have written as mu naught by 4 pi. This mu naught by 4 pi is like a proportional constant in physics, and it has been taken as 10 power minus 7. That is, mu naught is 4 pi into 10 power minus 7 into, we have written I dl sin theta upon r square. Right. So here what is meaning of this all elements? See, we have 2 quantities here, I dl sin theta and r. Suppose if it is a straight conductor, for example, you take a straight conductor. When we take a straight conductor, what is this r? This is very important here. R is the distance of the point where we want to find the magnetic induction due to this current carrying conductor. Okay, suppose this conductor is carrying current I, say upward. Suppose I want to find the magnetic field at a point P. Suppose this is my point P. First I have to select where is my origin. That is very important, because position vectors, these are all vectors, isn't it? So when you talk about vector, first we have to select what is our reference point. Also we call it as origin. Suppose for example, this is my current element is here. So this is my origin. I am taking this is my origin, say O point. For example, there is a O point, a reference point. Now, when I join this P point to O point, this is we say the position vector of the P point, that is OP is the position vector of the point P in the space, right. That means this we write as R vector, that is our R vector. So, when you select that, when you draw that R vector, there must be an origin, that is very important, the reference point must be there. So, because when it is a straight conductor, there won't be any issue here, you don't have any problem. But when it is not a straight conductor, when we are talking circular loops, like for example, now we are going to take up that article, we have to select first where is the origin, means where is our reference point to draw that position vectors, isn't it? So, for that, now see that Biot-Savart law what we have done. This is our origin, this is our position vector of the point. Then what we have done is, we have taken shortest distance from the point where we want to find the magnetic field due to this current carrying conductor. So, this we have taken as D, shortest distance. That shortest distance won't change, but R can change, because whenever this point changes, R value is going on changes, and whenever my reference changes, R value is going on changes. So, where is that theta now? What is that theta value? Theta is the angle made by my position vector with the current element direction. So, this is my current element direction, isn't it? I am taking, this is my IDL, my current element vector. This is my current element vector. So, this position vector is making an angle with our current element. I told you current element is similar to a charge in our electrostatics. Whatever the effect of a charge in electrostatic, same effect will be produced by IDL here. Their charge at rest, that will produce electric field, but here IDL is the current element that will produce a magnetic field at our desired point. Okay. So, that is meaning of this theta, and that is the angle what we have taken sine of that theta. So, that is very important here. Now, in vector form, see how we are going to write this now. So, it is equal to, we can write now, this is magnitude. So, what I have to indicate now? I have to indicate what is the direction of this dB, means that magnetic field. For that, we know already we are going to use a unit vector, because unit vector will indicate the direction. Therefore, we will write like this, dB vector is equal to mu naught by 4 pi into I dl is a vector into sin theta into R unit vector divided by R square. So, that R unit vector will indicate the direction of the magnetic field at the point P. So, how it comes in vector form now? That I can write like this also, because what is our unit vector? How do we find the unit vector? So, mu naught by 4 pi into I dl, this sin theta, R unit vector is R vector divided by magnitude of R vector. Therefore, this I can write R vector by magnitude of R vector divided by, what is this R? That is also same as that magnitude of R vector. So, when it comes to this form, it will be like this now. So, mu naught by 4 pi into, we can write now, see this, IDL sin theta, R we have no. So, this we can write now, IDL cross R vector divided by or upon R into R square into R, that will become magnitude of R cube. right? This is our Biot-Savart's law in vector form. Biot-Savart's law in vector form. So, in higher level problems, maybe sometimes in JEE Main or JEE Advanced, they may it will be very, very useful for us. So, this is our Biot-Savart's law in vector form. So, that will be in vector form. So, therefore, you have to remember this in vector form. Okay. So, this is Biot-Savart's law in vector form. So, that you have to keep in mind. So, if you are very serious about scoring advanced or some other exams, then this will be very, very useful for us, and you have to keep this in mind, right? Now, what is the direction of this dB vector now? See this? Mu naught by 4 pi is like a constant, proportional constant. R is only a number because it's only magnitude of that position vector. So, where is the vector form? IDL vector cross R vector, isn't it? That means the direction of our dB vector will be decided by the direction of IDL cross R vector. Now, recall our vectors, cross product of vectors. So, what is the direction of cross product of vector? Cross product we call it as vector product also, because it is the resultant of those two vector is also another vector. And how do you find the direction of that vector? See here, suppose if we are going to take cross product of two vectors, A cross B, let us say. For example, we have A vector cross B vector is equal to, we will write C vector, no? A cross B is another vector, that vector we write as C vector. So, how do you find the direction of that vector C? By using our right hand thumb rule. I told you the easiest and very common we are going to use is right hand thumb rule. That means here first we are going to take A vector, suppose this is our A vector, then this is our B vector. So, they may, B vector makes an angle theta here, then take your right hand, stretch the palm, keeping the thumb perpendicular, Now, keep our palm parallel to A vector, just see this, keep our palm parallel to A vector, curl the fingers towards B vector, see this, curl the fingers towards B vector, then the thumb indicate the direction of the C vector. Means what? This C vector is mutually perpendicular for both A vector and B vector. A and B are in one plane, and C vector is mutually perpendicular to that A vector and B vector. So, that is the direction of our cross product. So, see here, in this case IDL cross R. IDL is like A vector and R is like B vector. So, what you have to do? First you see where is your IDL vector. We know IDL vector is the tangent drawn at the point to the conductor. So, keep your palm in the direction of that IDL vector and stretch the thumb perpendicularly, then curl the finger towards our R vector, right. Then our thumb will indicate dB vector. Thumb will indicate the dB vector. For example, see this diagram. This is your IDL vector, isn't it? So, what you have to do now? You keep your palm like this, parallel to IDL vector, then curl the fingers towards your R vector. Then this is your direction of the magnetic field, that is dB vector. Direction of the dB vector. So, if the if thumb is coming towards us, that means the field is coming out of the plane, and if thumb is going away from us, then it is going into the plane. or into the page. Suppose if you take your notebook, if thumb is coming towards us, when you curl the finger, thumb is coming towards us, then this will be our field is coming out of the plane. If it go away from us, then it is going into the plane, means into your paper of your notebook. So that is a way to find this dB vector. So I told you already, when it is a straight conductor, it is very easy to find the direction. So if it is a straight conductor, we are using right hand thumb rule. I told you the method also. So what we have to do? We have to imagine that we are holding the conductor in our palm, and our thumb should be in the direction of the current, electric current direction, right? Then see this curled finger will indicate the direction of the field. If the fingers are coming, this is field lines. These are field lines which are concentric to the conductor. Concentric to the conductor. So when you curl the finger, if the finger, see this now, this situation. When I take this conductor, see here on this side, left side what is happening? Fingers are coming out of the plane, means they are coming towards us. That is, here the field is coming out of our plane, out of the paper. And see this side, they are going into the plane. Fingers are going into the plane. That means the fingers are going away from us. That is, the field is into the plane of the paper. That is the easiest way to find the direction of the magnetic field induced. Okay. Suppose for example you take this case. So it is a straight conductor. See this. See how we are doing now? We are imagining that we are holding the conductor in our palm. Then see, keeping this thumb perpendicular in the direction of the current. Then see that fingers, how they are. Fingers are coming out of the plane at the left and going into the plane at the right. Means here the field dB is into the board. Whereas on this side, if I am take the same point, it will be out of the plane. So that is a way to find the magnetic field very easily. Right. So now let us come to our magnetic field at an axial point of a current carrying loop. Just like a ring only, but we don't say ring now, we say it is a current carrying loop. Therefore, for that, just see here, we will take one loop. So we take the loop now here. So we are taking one loop, current carrying loop. So this is our current carrying loop, right? So current carrying loop here. So this is the loop. So this is the current carrying loop having center at O. So let us say center at O. This is the center of the loop O. Now, now here we want to find the magnetic field or magnetic induction at a point on the axis of the loop. Axis means it is a line passing through the center and perpendicular to the plane of the loop. See, loop is actually on the board. Loop is on the board. Means, just see here. Suppose this is the loop. For example, this is the loop. This is our current loop. This is the center. Now you take a line passing through the center and perpendicular to plane of the loop. See, this is the plane of the loop. Then you have to take a line perpendicular to the plane of the loop. That is our axis of the loop. This is the axis. So our loop is like this, no, on the board. So where is our axis actually? It is perpendicular to the board. Suppose if this is xy plane, our axis will be along the z axis. along the z axis, that is our axis. So here this is our axis now. Okay, now we want to find what is the magnetic field at this point. Say point is P. Our point is P. Right. Now select our current element first, because loop is having so many current elements, not one, so many current elements will be there. For example, for convenience, we are taking current element here. This is our current element. That is the current element. So we take, this is our current element. Okay, that is our current element, right? Now this is our current element. Now this is our loop. We take, this is the current element. So this is our current element now. Now to find where is theta, what I told you just now, what is the first step? Where is our origin? That is reference point from which we want to measure all the distances. Where is our reference? That our reference is the center of the loop. First join the current element to the center. The current element to the center. First join that. So what is this? Radius of the loop. Radius of the loop. Now join our point to the current element. This is our current element, IDL. This is our current element, IDL. This is our IDL. Right. Now join our point to the current element. So that is our R. This is R. Let us say this distance is x. Follow the point here. How to measure the angles? That is, now where is our theta? What is that theta now? Theta is the angle between the radius vector and the position vector. That is, this is our angle theta. That is our angle theta. And in this case, theta is how much? 90 degree, because this is our radius vector and this is our tangential vector, that is the tangent, because we have joined a point of the circle to this point, means this is like a tangent and this is like a radius. Therefore, in this case, theta is equal to 90 degrees. Theta is equal to 90 degrees. Now we want to find what is the direction of the magnetic field at this point. So now see this is our dl vector and this is our r vector. This is r, isn't it? So when you take our right hand thumb rule, again we can know what is the direction of the field. We know already that field will be perpendicular to the plane in which IDL and R vector are existing. They are on the board. Therefore, our field will be perpendicular to the board. It is not exactly perpendicular here, because this is making an angle here with the x. Therefore, our field will be now this one. This is the direction of the field. So here, suppose this is our perpendicular. If this is the perpendicular, we take perpendicular here. Suppose this is a perpendicular, we draw at this point, that is the point P. So this is the perpendicular we are drawing here. So that I will take as a line. So suppose we are drawing, this is the perpendicular. So this is the perpendicular, let us say. Right, perpendicular. Now our field dB our field dB will make an angle theta with the point at point P. But here for this element there is a corresponding element in the bottom also, because ring is symmetry around our x-axis. This is like our x-axis. So, ring is symmetric around x-axis. That is, for every element at the top there will be a corresponding element at the bottom. Corresponding element at the bottom. That means what? Due to this element, if this is the direction of the field, here there is one more element is there. That field will be in the opposite direction, just opposite to this. Isn't it mutually perpendicular? Therefore, our field due to bottom element will be in this direction. Right. So, this is our angle theta, phi, not theta, sorry, phi. Then this is also phi. So, this angle also will be equal to phi. Right. Now, when this is phi, we know this one C. These two are mutually perpendicular to each other. Mutually perpendicular to each other. This is phi, then we know this will come 90 minus phi. Therefore, again this one and this one are perpendicular. Therefore, again this will be also phi. Right. Suppose this is our dB. dB here. This dB we can resolve into two components now. One along y-axis, this is like y-axis, that is dB cos phi. This is our dB cos phi, and this is our dB sin phi. But here also, due to this, there is similar elements are there. There are similar element dB and dB sin phi. So, dB cos phi, they are going to get cancelled with each other. So, only field is due to the dB sin phi element, that is like x component of dB, y components are gets cancelled here, and only due to x component there will be a field at this point because of this current element. Because of this current element. Therefore, our resultant field equal to, we can write dB dash, let us say, equal to dB sin phi. dB sin phi. Now, what is the magnitude of this R? What is the magnitude of R? So, magnitude of R will be equal to how much? This is a right angle triangle. This is a right angle triangle, isn't it? Therefore, this is like hypotenuse, this is like adjacent side, this is like opposite side for phi. Therefore, R is equal to, we can write square root of, so R is equal to, can be written as, so R is equal to, we can write under root R square plus x square, isn't it? So, magnitude of R equal to under root capital R square plus x square, where capital R is radius of the ring, that is radius of the loop, and x is the distance from center of the loop to the point where we want to find the magnetic field, right? And what is sin phi? What is sin phi? Sin phi equal to R by x. So, here we can write, so sin phi equal to R by capital R by small r. So, sin phi equal to capital R divided by small r. Now, we know what is dB. So, write the value. So, dB is equal to mu naught by 4 pi into I into dl into sin phi. Sin phi is how much? Sin phi capital R by small r upon r square. R square. R square means capital R square plus x square whole square. So that will be r square plus x square. Right. This r also will come to denominator. Therefore, that will become mu naught by 4 pi into I dl upon here capital R. So upon we have r square plus x square, r square plus x square into under root, r is under root, r square plus x square. Therefore, by 3 by 2. By 3 by 2. Next. So what we have here, dB is equal to mu naught by 4 pi IDL sin theta. Sin theta already we have taken 90 degree. Therefore, it will be equal to 1. So now we can write here mu naught by 4 pi IDL into R divided by R square plus X square whole power 3 by 2. Here this is a constant, I is a constant, capital R is constant, and position X is also constant here. So only variable is length element. Therefore, we have to integrate now to get the total field. Therefore, to get the total field, we are going to integrate this now. So we are going to integrate here. So integral of dB is equal to integral of mu naught by 4 pi into IDL into capital R divided by R square plus X square whole power 3 by 2. So all are constant except dl. Therefore, now we can write that as integral of dB is B. So B is equal to total ring due to total loop equal to this we can take outside mu naught by 4 pi into I divided by R square plus X square whole power 3 by 2 into integral of that we can write integral of dl. What is integral of dl? Total length of the loop, no? What is total length of loop? Circumference. Therefore, that will be equal to, we will get mu naught by 4 pi into I divided by upon R square plus X square whole power 3 by 2 whole power 3 by 2 whole power 3 by 2, right, into 2 pi r into r. Already here one r is there. So into r, isn't it? Therefore, now what you will get here? Pi gets cancelled 2 times. Then our final answer is mu naught into I into r square divided by 2 into r square plus x square whole power 3 by 2. So this is our the magnitude of the magnetic field due to a current carrying loop at an axial point at distance x. Mu naught into I into r square by 2 into r square plus x square whole power 3 by 2. Here the symbols are very important. Capital R is the radius of the loop. Generally sometimes they will take A also as radius, and x is the distance along the x axis that is shortest distance from center of the loop to the point P, that is the x distance you can say or shortest distance which we have taken d previously for straight conductor. Therefore, that is our final formula for magnetic induction due to a current carrying loop at an axial point. So, this is very, very useful for us. From this, when we want to find the magnetic field due to arc of circle or semicircle or quarter circle, we can utilize this derivation, right. So, that is the magnetic field due to a current carrying loop at an axial point. Okay. So, that is the field, and the way calculate the field may be useful for your board exams. IIT exam, the method is very important. For our JEE, MSET, NEET, advanced, method is important. How we select element, how we are integrating, that is all very, very important here. Okay. So, that is the magnetic field due to a current carrying loop. Suppose if the loop is not complete, but arc of circle, that arc make an angle phi at the center of the circle. From this you can generalize. Now we can generalize this derivation. That is, for example, we have an arc of circle, a conducting loop, let us say arc of a loop. So, this is an arc of a loop. Okay. Now, this is our current carrying loop. This loop making an angle, say phi at the center of the circle. At the center of the circle, right. So, it is making an angle phi at the center of the circle, this O point, which is center from which this is cut out. Okay. Then from this we can generalize the field will be B is equal to mu naught by 4 pi into I by R. Suppose R is the radius, I by R into phi. So, that is for an arc of circle. Arc of means a part of the loop. If we want to find what is the magnetic induction or the magnetic field at the center due to arc of circle, okay, is carrying a current, right. So, I is the current carried. Then this is our generalized formula that we can use here to find what is the magnetic field induction, or generally we call magnetic field due to arc of a circle. So, arc of the circle. So, that is important for us to find, because most of the time examination they will ask a combination of arc of circle, straight conductors, all combination they will ask. In that case we have to combine all the fields by vector notation. We are going to combine and we will find what is the resultant field at a required point. Okay. So, that is about the magnetic field induction or magnetic field at an axial point. So, tomorrow we will solve problems based on this. All models, 2-3 days we will solve problems based on these concepts. Okay. All variety of problems we are going to solve. Okay.